Okay, we're in the middle of proving a theorem that says connected if and only if. This essentially says that E is an interval. So I'm going to assume that it's an interval, and I'm going to prove that that it's connected. And I'm going to do that by a theorem that says that if E is the union of A and B, then E is connected if and only if there is a sequence in A that converges something in B, or vice versa. And the strategy for the proof is kind of cool. So let's assume that I have E is equal to some disjoint A intersect B, like so. A intersect B is empty. I'm going to prove that either one of these two things happen. Either your sequence is in A, converges to something B, or vice versa. So these have to be non-empty. A and B have to be non-empty, so I'm going to let A naught and B naught be just any 2 points in A and B respectively. What I'm going to do then is I'm going to look at its midpoint, which maybe I'll call M0. One of two things will happen. E is an interval. Whenever you have a point between two things in E, it also has to be in E. Now E is the union of these two, which means that either this belongs to A, in which case I get a new picture that's going to look like this. A1 and B1, where my B0 just equals, my new B1 is just going to equal B0, and my new A1 is going to be equal to M1. Or it's going to look something like this. My A1, I'm going to redefine A1 to be A0. My midpoint here is just going to be what I'm going to call B1. So if the midpoint belongs to B, my interval is going to look like the left half. If my midpoint belongs to A, it belongs to the right half. It has to belong to one of them since E is equal to the union. And so this is how I'm going to split it up. So now I have, whatever the picture is, let's say it's maybe this one. Now I have an interval half the size. So let's call this one I0 equals A1, A0, B0. My I1 equals A1, B1. And similarly, I can create I2 by looking at the midpoint of this one. If the midpoint's in B, I'm going to take the left half here, and I get A2, B2. Or if the midpoint's in A, I'm going to get, this is going to be my new A2, and that's going to be my B2. So I can create a whole nested sequence of ANs and BNs like this. And you can probably guess where I'm going with this, is that now by the nested interval property, I get some sort of an X that belongs to the intersection of all these things. So, but what happens, right? Eventually, right, the length of IN is equal to the length of I naught over 2 to the n. Eventually, that's going to be less than epsilon for any epsilon that you pick. So, right, fix epsilon. Then pick n such that this is true. Then AN, right, this is the length of AN, BN. AN minus x is going to be less than epsilon, and BN minus x is less than epsilon. So I'm going to get, so basically I get all my ANs are going to converge to x, and all my BNs are going to converge to x. But my x is in all these intervals, and these intervals are completely contained in E, because my E basically is a big long interval as well. So if x belongs to B, since E is the union of A and B, then I'm good. Then I get all these ANs converging to B, which is what I want. So I can use that theorem that says I got these XNs that are in A, and they converge to something in B. Or I can get these BNs converging to X if X is in A, in which case I get BNs in B conversion to X in A. So the theorem in the book says that this is exactly the condition we need to show that E is connected. And so we've done it. We are done.